we will discuss what diazonium salts, how it is formed and its reactions. Okay, so let us start. So this is benzene diazonium chloride. There is electrostatic force of attraction between the nitrogen and the chlorine. Okay, so how is it formed? By diazotization. Okay, I start with aniline and give it a condition of NaNO2 in presence of HCl, keeping the temperature to 0 to 5 degrees Celsius. This nitrogen and this nitrogen, see, it is a shortcut way of remembering things. So these two nitrogens, they combine to form the diazonium salt. Alright, and this compound is resonance stabilized. How is it resonance stabilized? Because you see there is a positive charge, so like the pi cloud will go to neutralize the positive charge nitrogen. So this is how it exists in comparison to an aliphatic diazonium salt. I hope it is clear. This is the only method of preparation that is there in the syllabus for preparation of diazonium salts, that is by diazotization reaction. Okay. Let's straightway go to its chemical properties. I will put the diazonium salt in the center and create a flow chart whereby you will understand what happens. Basically this is a very good leaving group. So what will happen is that suppose I try to react it with Cu2Cl, then what will you get is a nucleophilic substitution will happen. The Cl will get substituted here. This is the point where the nucleophile comes in. Two is knocked out as nitrogen gas. Okay, so this is Sandmeyer's reaction. Next, if you use Cu2Br2, what you will get, yes, I know you know the answer, I don't have to do it. Okay, but still, you get bromobenzene with nitrogen gas being involved. So in general, I can put this as X. So, giving ourselves a benefit of doubt, like if it is bromine, so naturally the side product will again be Cu2Br2. So next, if we see I have got a chlorine, I have got a bromine. Now I want to get fluorobenzene or iodobenzene. What do? So I put potassium iodide and the same reaction happens and you get iodobenzene along with nitrogen gas and Ki. So why didn't we use Cu2I2? The reason being Cu2I2 is unstable in aqueous solution. That is the reason we haven't used Cu2I2. I hope that is clear. Next, yes, of course I would like to prepare fluorobenzene, but hold on, it is not a one-step reaction, it is a two-step reaction. Okay, so we put fluoroboric acid HBF4 where there is an anion exchange reaction. Okay, there's an anion exchange reaction, you need to write this intermediate, mind it. So you get N2 plus and BF4 minus where that has occurred an anion exchange along with HX. Only if you heat it, there is a fluorine coming in and then you get fluorobenzene. Okay, the fluorine migration is there followed by evolution of nitrogen gas and formation of BF3. These compounds exist. So this is how we prepare all the haloarenes from diazonium salts. Let's go on to something else. Let us put water now and warm it a little. So here we have the nucleophile. You know that water always breaks up as H plus and OH minus most of the time. So naturally you see the nucleophile, do you? Yes, OH minus, the nucleophile. So you know the product, very good. So you get phenol and nitrogen gas evolved along with HX. So see this flowchart, I think will help you memorize this entire thing and mind it. This is a very easy way of getting all the reactions right. These reactions so easy because we always understand that nitrogen here evolves out as nitrogen gas. It's a good leaving group. Let's go to the next reaction. Say I want benzene. From benzene diazonium chloride, I want benzene. That means it has to be a hydrogen here which is there. So I need a very good reducing agent, and the good reducing agent is hypophosphorus acid, which is H3PO2. This in the presence of water, which is H2O. I break up this water as H and OH. See the concerted mechanism which I'll do. The OH comes here. So this hydride transfer happens I need a nucleophilic hydrogen, which is a hydride. So the hydride transfer happens. So I get benzene along with nitrogen gas. Yes, the hydrogen and the X goes out as HX. Yes, well interpreted. And of course, if this is a reducing agent, it will get oxidized. So see how the structure is. OH, you have an OH input from here. Okay, and an H. So see, the reducing agent has got oxidized. This is hypophosphorus acid converted to H3PO3, which is phosphorus acid. Okay. Next, the next reaction we'd like to go is a similar kind of reaction. See, I have a second option of getting benzene from benzene diazonium salt. We use ethanol. Have you heard of ethanol ever being a reducing agent? No, no. So this is one of the unique reactions. Ethanol, this is a good reducing agent. Once again, there is a hydride transfer. We are giving you the product, which is benzene. And what happened to this? See, this H and this X went out as HX. So what about the alcohol? If it is a reducing agent, it will get oxidized. And it will get oxidized to what? Yes, did you say aldehyde? Correct. So these are two methods by which you can get benzene, either using hypophosphorus acid or by using ethanol. Correct. This is a unique reaction you have to remember. I hope you all are noting it down, otherwise this practice is of no use. Okay, let's go to the next set of reaction, which is using copper along with HCl. Copper powder along with HCl. Copper powder along with HCl just behaves like a Sandmeyer's set of reaction. So here also see the Cl factor, which is the nucleophile. You focus on the negative part. What is the negative part in this entire thing? Hydrogen is positive, copper is positive, it's a metal. So the negative part is Cl. So naturally you will get here chlorobenzene once again. Okay, with nitrogen gas being involved. And the HCl coming back, HX coming back and being recirculated. Okay, similar kind of reaction is there, and that is with copper and HBr. What? I shouldn't do this reaction? No, just check your product and hence I'll write it down. Yeah, you know it, I know it. So I can feel it, you know it. Yes, same logic. Copper powder along with HBr, nitrogen gas is being evolved. Got it? That's good. The third set is over. Let's copy or understood. Both. Yes? Nice. Let me tell you what do I want ultimately. What I want is nitrobenzene. Do I have a technique of getting nitrobenzene? Okay, right from benzene diazonium chloride. So the first step for this reaction is reaction with fluoroboric acid. HBF4 is called fluoroboric acid. So fluoroboric acid, yes. Do you remember the anion exchange reaction? Let's do it. The anion exchange reaction. That you cannot avoid. You have to write this step. And the intermediates is a must. So BF4 minus. Yes. Next, in order to get nitrobenzene, I've got to play around with the reagents. I need a nucleophilic NO2, and that is in the form of NaNO. This is a nucleophilic NaNO. So this entire series is about nucleophilic substitution reaction. Huh? So let's take this negative NaNO2. Nucleophilic substitution happens. Do you require heat? Yes, you need a copper catalyst and heat. Right? So instead of fluorine being substituted, because you have put a better nucleophile, which is in the form of NaNO2, you will get this product. Okay, where NO2 has substituted nitrogen gas in the side product of the reaction, and you have NaBF4. You understand? Na is left, BF4 minus is left, so you get NaBF4. Copper is the catalyst of the reaction. So this is how you can get nitrobenzene, starting with diazonium salt. Last but not the least, we'll have to do the coupling reactions. So let's go on to the coupling reactions. Like, what is the trick and how do you know that ये reaction coupling reaction है और कुछ नहीं है? So you will understand that. See the way I'm writing this benzene diazonium, but I'm drawing the structure of it. नहीं तो मजा नहीं आता है ना ये समझने से कि कौन सा बॉन्ड ब्रेक होता है, कौन सा मेक होता है. तो if you get an aromatic compound given to you, okay, aromatic compound given to you with an electron donating group. So what will happen is that here the para position is negatively charged due to resonance. So here the negative para position will attack the nitrogen, and here the triple bond. Nitrogen's valency to 3, it's 4. So it has to come back to a valency of 3. So it tries to break the bond. So let's write the product. So this is a coupled product. This is one ring which we have. And then this is the second ring which we have. Basify the reaction. Okay, so once you basify the reaction, you get a coupled product where the para position of phenol is attached to the nitrogen of the diazonium salt. Along with, you understand that there is a hydrogen at this point. This hydrogen and the Cl will go out as HCl. So this is called para hydroxy azobenzene. And you know, how do you remember the color of this compound in case it comes as a para-based question? O, you see now, O stands for this orange color dye. This is a dye which is orange in color. So anytime you want to go ahead with a test of anilines, you're distinguishing test between aniline and methyl amine. Both are primary amines. So how do you distinguish? You prepare this diazonium salt, okay, and after preparing the diazonium salt, add this bulky compound which will give you a dye, which will not happen with the aliphatic amines. I hope you understand what I said. So you get this. There's another reaction of this type, where now time let it be aniline. So draw the flat rings whenever you are doing the coupling reaction. So we have aniline. Once again, because it's an electron donating group, resonance creates a negative charge at the para position. Same attack this way. So the only thing I have to do is replace the OH with an NH2, and now I get the product. Alright, same thing. So with the side product, once again the hydrogen and the Cl will go out as HCl. So this is para amino azobenzene, which is a yellow. So any of these coupling reactions, the previous one with phenol or this reaction with aniline, you can take up to distinguish between aniline and any aliphatic amine. So this brings us to the end of diazonium salts. And